Hello and welcome to the Introduction to Capacitors lecture. In this lecture, funny enough, we're going to be looking at capacitors. Here's a big one and here's a smaller one and just some different sizes. Now, we're going to be looking at capacitors more later on. This one's more of an introduction, but the general gist of it is a capacitor is a device that can store energy. So we can connect it up to a power supply and we can shove all these electrons in there and onto one side of it, and then we can get all the electrons off the other side, and that can give us a difference in potential, so positive and negative, so it can store a charge. Let me show you how that works. I'm going to turn this light off. So I have my capacitor here. It's got a positive and a negative connection, and I've got this really low voltage 6-volt power supply here. So at the moment, this is discharged. It has no charge on it. So when I connect this LED to it, nothing happens. However, if I was to charge this up, so positive lead goes into the center there, negative lead connects to the outside, this capacitor is now charged up to 6 volts. Let's get this LED again, connect it up, and you should be able to see the LED is now shining quite bright. But notice how it's getting dimmer and dimmer and dimmer. That's because the capacitor is discharging and discharging and discharging. Eventually it'll get to 0. In fact, if I connect these leads together, it'll go straight to 0. So now the LED will be off. Now let's see something else pretty cool. Let's charge it up again. So positive lead to in the inside, the negative lead to the outside. Realistically, I don't have to hold it there for that long. It's going to charge really quickly. Now watch what happens when I short the leads together. The thing is, with a capacitor, we can store a charge in it, but it can release that stored charge really quickly. Because it releases it so quickly, we can generate sparks like that. So let's get some light back on. Alright, here's a picture that I took with a camera, which that's how you take pictures, I guess. We've got different types of capacitors. This is the one that I was playing with there. We call it, it's categorized as an electrolytic capacitor. We have a few different types of them, so some big, some small, different values. Some of them can be used with high voltages, some can be used with low voltages, and we'll talk about that a bit later. We also have ceramic, that's these little guys here, some polyester capacitors, and then we've got a little tiny surface mount. So just as we spoke about surface mount resistors before, you can get surface mount capacitors as well, which means they don't have legs that go through a circuit board, they just sit on top of the circuit board. Now again, a capacitor is a device that stores charge. It's got two connections, as you can see here, and in fact some capacitors, like this electrolytic, it tells you the negative connection, the other side is positive, so you must connect it up the correct way in your circuit. But then other ones, like this ceramic, it doesn't matter which way you connect them up. It doesn't have a positive or negative, you can swap them around and it's all fine. So depending on how they've actually made the internal structure of the capacitor will determine if it is polarized, so it has a positive and negative, or if it is not polarized. Now, what can we use capacitors in? Well, as I said, they can store a charge, so they're really good to be used in power supplies. In fact, here's my old MacBook power supply that blew up. This particular one has a big capacitor there, it has some smaller capacitors over here. It's got a whole load of surface mount capacitors on the back of the board as well. So they can store energy, store a charge, so they're good to provide power. What else can they be used for? Well, if you've ever tuned in a radio station before, if we go back to the really old school cars of like the 70s and 80s, do you remember tuning in the radio where you'd turn the dial and the little needle would go back and forth to tell you the radio station? What you're actually doing when you rotate that is, you're actually rotating a special capacitor called a variable capacitor. You're changing the amount of capacitance or the amount of charge that it can possibly hold, and that's how you tune in your radios, and we'll talk about that more later on. We can use them in cameras, so your camera flash. So because our camera flash needs a lot of energy really quickly, we charge up a capacitor and then we supply that to a special bulb that will give you a flash. They're in computers, they're in calculators, they're in watches, they're in mobile phones, they're in pretty much any electronic device, I would have to say. Let's have a look at the internal structure. So in its most basic form, a capacitor just has two pieces of metal, or two metal plates as I've written here, separated by some kind of insulator. We call this insulator a fancy name. It's called dielectric. But that dielectric could be any insulator. It could be air, it could, sometimes they use beeswax, it could be mica, it could be all sorts of, you could even use paper there if you wanted to. All sorts of materials, as long as it is provides an open circuit between the two plates. Because you saw what happened when I shorted the two connections together, it gave me a zap and then it completely discharged. If the two plates were ever to touch, we'd get that zap happening again internally, and it would discharge. So that's why it needs to be an open circuit. Now, depending on the type of stuff we put in here, it's going to determine the value of capacitance we get, or it's going to play a part in the amount of capacitance that we get, or the ability of the capacitor to store a charge. We then have different circuit symbols. So just like we had a resistor which looked like this, we have circuit symbols for capacitors. So this one here is a normal capacitor, which would be non-polarized like a ceramic or one of these polyester ones. However, when we're talking about this guy, an electrolytic, you're going to have like a plus sign and perhaps one of these curved leads. That tells you that it is polarized, and it's important to pay attention when you connect it to a circuit that you get the negative and positive around the right way. Physically on the capacitor, it shows you a line with little negative symbols in it. That shows you the negative connection. The other side is the positive. Now finally, I don't have one here to show you, but you have variable capacitors. Just like a variable resistor, you rotate it, and as you rotate it, the capacitance changes. You could have a very small capacitance, and then you can go up to a very large capacitance as well. Now, I'll tell you this now. Capacitors are, so I'll write it, ooh, that's a bit big. So capacitors are measured in farads. Farads, after Michael Faraday. So if we're talking about it, in fact, let's have a look at this one. This one's quite a large one. If I have a look, it is rated at 5,600 microfarads. A 1 farad capacitor would be huge. In fact, if anyone has anything to do with car audio systems, you may have bought a 1 farad capacitor before, and you connect it up to help your subwoofer actually get to work properly. So huge capacitor, physically a very large capacitor if you've got 1 farad. So generally we're talking in the microfarads. This little one here would be in the nanofarads. We can even get really tiny ones which would be in the picofarads. And we have all these different values for all different applications, and they suit all different purposes. So they measure in farads, and we'll look into that more later when we do some calculations. But what actually happens with a capacitor? Well, I'll give you a very general intro here, but again, we'll have some more videos later on that goes into some calculations. What I've got here is a resistor here. That's called the R charge, or the charge resistor. When we flick this switch here, we're going to have electrons flowing this way, and that resistor there is going to limit the amount of current. So we can actually slow down the charging speed with that one. Once we've charged the thing, we're going to close this switch. That's our discharge switch, and we're going to discharge the capacitor through the discharge resistor over here, which is kind of what I was doing with the LED. So we charged it up with the power supply. However, I didn't use a resistor to limit the current, so it charged really quick. And then I connected an LED, that was my output, and so it discharged, and it kept getting dimmer and dimmer and dimmer. So let's have a look. We have a charge switch. Let's get rid of that, and let's close it. Now remember, this is an open circuit in here. Open CCT to represent circuit. What we're going to have is, let's get this a bit thicker. We'll have electrons starting from the negative plate. They'll go through the charge resistor, and they're going to start building up on the bottom plate here. Now when this thing is discharged, there is no potential difference between this plate and this plate. The reason for that is the electrons, the atoms on each of those plates are electrically neutral. There's the same number of protons as there are electrons. So if we now apply a potential difference with our power supply, we've got a whole heap of electrons over here, and they are going to be pushed onto this plate. So if we start receiving electrons on this plate over here, we now have an excess of electrons. With an excess of electrons there, it's going to start to build up a negative charge. But what happens on the other plate? Well, since we've got positive connected here, we've got all of these free electrons which are going to be attracted to the positive end of the power supply. So these electrons will leave there. If we had atoms that were electrically neutral and now electrons are leaving those atoms, we've now got more protons than we have electrons. Therefore, we start to build up a positive charge here. So the capacitor, with the power supply connected like that, negative down the bottom, positive up the top, we're going to build up a charge, positive here and negative there. And eventually it'll charge up to the full power supply voltage. If this was 5 volts, this will charge up to 5 volts. We can slow down the rate at which it charges by just changing this resistor. Increase that resistor, you slow down the current, it takes longer for this thing to charge up. If you don't have a resistor there at all, it'll charge really quickly. Okay, so once this thing is charged, just going to get rid of all this. We will get rid of that. There we go. So I've open circuited this again. Now, because I don't have a complete circuit here to discharge the capacitor, it will hold on to its charge. Just like when I charge this thing up, I disconnected it from the power supply, it's still fully charged. I need to give it some discharge path for the electrons to actually go to the other plate to get rid of that charge. So in this case, I need to close this switch. Oop, keep doing the wrong thing there. So we close that switch, go back to the highlighter. Remember, this built up a charge, negative, positive. And what I really should be doing here is fixing up all these. So when it charges, we actually get all the electrons leaving here. So it leaves a whole heap of positive ions. That's how it gets a positive charge. And then all the electrons come from this side and they start filling in, or we start to get a whole heap of excess electrons going on here. Whoops. Therefore we get a negative charge there. That's how we get this more positive than this. We push electrons into here and then electrons leave there to go to the positive. They're attracted away. Now, we have closed this switch over here. We've now got a discharge path. Electrons will leave there, go up through the load here, which is our discharge resistor, or the load could be an LED, it could be a motor, it could be all sorts of things. And what's going to happen is we're discharging, which means this is slowly losing electrons and this is slowly gaining electrons over here. So losing electrons over this plate and gaining them over here. Eventually what will happen, hopefully you can see, eventually we're going to lose so many electrons and they're going to go to the other plate that we're going to get to that point of equilibrium again, where we've got an even number of electrons as we do protons in every single atom. Therefore, this becomes neutral again because it gains electrons because it was positive before. This one loses electrons and it therefore becomes neutral again by getting rid of all the excess of electrons. So then we've got zero charge left, it's completely discharged, and we have no current flow in the circuit anymore. So that there is the general gist. Okay, I was going to show you on a different page the discharging cycle, but I can just use this one page. So we have a capacitor. If we short that together, it's definitely discharged. It has no difference in potential, or it doesn't have a build-up of electrons on one plate and a build-up of positive ions on the other. So this is not going to do anything. However, I connect it up to my power supply. Here's my 6-volt power supply in this case. Now that's already charged really, really quick if there's no resistor there. Because there's an open circuit there, there's no way for that to discharge. So when I get my LED again and connect it up, you'll find it turns on. And it gets dimmer and dimmer and dimmer. because what's happening is the electrons from the negative plate are going through the LED to the positive plate, making the positive plate a bit more negative. Eventually they both get to the point of equilibrium and it's completely discharged. Alright, well, I think that's a bit of a good introduction to the capacitor. As we go through our next lectures coming up, we'll do some calculations and we'll work out a little bit more about how these capacitors in conjunction with resistors and the power supply actually work, and just work with some values with that.